Hello, today I'm going to talk about one of my blunder in statistics and cooperative game theory. So I think it's a good like introduction to a certain problem and problem solving skills. So one of my tasks was to implement this fancy formula. I'm going to explain it in detail, don't worry about it. In Python, so I'm decent in Python, so I think I can implement that well. I had to work this in parallel with my main work, so it was like a side task. And in this task, I had big trouble to implement it, and I'll explain why a bit after. So this let's look at the formula. So for all values of I between 1 and n, with n being a variable that is known, we compute the value sh called the Shapley value I, so I being here the value, so it's Shapley 1, Shapley 2, Shapley 3, etc. Divided by 1 divided by this, so this is n, so the number of dimensions. So if you are working with dimension 3, 4, it's just the division by that. So far it's not too bad. Here we have a t means the transpose, so it means that if you have a line vector it becomes a column vector, and if you have a column vector it becomes a line vector. So far not too bad. Here we have a matrix, a square matrix sigma that represents the covariance matrix, and the product between beta transpose sigma and beta is a matrix multiplication. So beta matrix multiplication sigma matrix multiplication beta. So if you did a bit of matrix algebra, so this shouldn't be too hard. So okay, here you have a sum. Okay, so let's look at this sum. So we have U being a subset or the same set as minus I. And now it can be a bit troublesome if you are not familiar with this notation. So I is a scalar, and we say inside the subset. So here the trick is the minus sign. The minus signs mean that if you have a set I, it means that it's 1 to n removed with what's inside this. So here, let's say I is equal to 3 and n is equal to 5. So it means that it will be all the numbers between 1 and 5, since n is 5, except the number 3. So it will be 1, 2, 4, 5. And if you have minus a set of things, like let's say a is 2 and 3, it means that minus a will be, with n is equal to 5, 1, 4, 5. So this is a subset, so we are summing over 2 to the power n with n, since we are summing over the set of subsets, and this has cardinality to the power n, with n being the number of dimension. So yeah, this shouldn't be too hard to get this. Here we have a binomial value. No, how is it called? Binomial coefficient. With on the top n minus 1, so the number of dimension minus 1, and the length of the set u, so it's just the number of elements. All of this to the power minus 1, so we're dividing by that. Shouldn't be too hard either. And we have a cost function c. Here we have a set, so u being a set and I being a set. This plus means it's the union of both sets. So since u and I are always disjoint by this property, since u cannot have the element I, therefore u plus I always means that it's the union. and U also. So cost is a function that depends on a certain set. This function is detailed below. So this C is called the cost function. So if we have a set A, the cost function of A is equal to the variance of the expectancy. How is it called in English? I don't know. It's the variance of the conditional expectancy of Y with respect to XA. So if A is a scalar, it means only the value xi, so x1, x2, x3. And if A is a set with multiple values, so let's say A is equal to 2 and 3, it means that it's the conditional expectancy of Y knowing x2 and x3. And we find this formula, so I'm going to explain it a bit later. We find this weird formula with a vector in which we take certain elements. So beta minus A means we take the elements that are inside minus A from the beta. For example, if A is 2, 3, therefore minus 2A is 1, 4, 5. So we take the elements 1, 4, 5 from beta. So we get a vector, but a vector that is shorter than beta. We do the same here. Here we have some fancy matrix multiplication, and like here we do a matrix multiplication. And we know n, beta, and sigma. So this is known. This has to be calculated. This is known. This is known. We just have to compute this binomial coefficient. The cost value, we have to compute the union of the sets. And here we have to compute this junk. So it didn't seem too hard when I first look at it. It's a, oh, okay, it's easy. Okay. So the problem is that I expect the sum of all the the Shapley values to be equal to the cost function of 1 to n, which I will show it later, is equal to 1. So the problem is that my algorithm was not going to 1, so when I was testing with a lot of values, so samples, normal distributions, I was not getting 1, and I should get 1 even when I'm not in a normal distribution, but at least when I'm on a linear model, I should have a 1, so I'll explain a bit later why this. So there was definitely something fishy about my algorithm, and I did not understand why, because it seems easy, like the notions that were inside were enough clear to me to implement it without having to struggle. And as I said, it took me around a month to overcome this problem. So my first instinct was to look at the formula, say, okay, maybe I did the matrix multiplication wrong. To look at the subset, so maybe I did incorrectly the minus I part, maybe I did the subset part wrong, maybe I forgot the minus 1, maybe I did wrong the plus, so the union here. So I thought it was that, and I also thought maybe I did the indices wrong, so maybe I did A instead of minus A, or vice versa, that I swapped something. So the indices in here, I was worried it was here, but all of this like this was correct, and I was shocked. I did not understand why, and let's see what happened later. So let's do a bit of conditional conditional game theory, also called cooperative game theory. So there is a slight difference between cooperative and coalitional game theory, but I am not sure I understand it quite well. So let's define a game that has a set of n players. So so we have n different players and a characteristic function that has values from 2 to the power n to r. In particular, this function v, v to the empty set means that it's the value of having no player in a certain coalition. So what is the value of no player? It's 0. What's the value of having all the players from the game in your thing. It's just the value. It's the maximum that you can get, because you can't have more value than something. So and we have value from 2 to the power n because we are going to the set of subsets of n, so it's correct. And if we have a set S, then the team of if we have a coalition, so a team of players, then V of S is called the worth of the coalition in game theory. So in 1951, Shapley wrote this junk. So it's 1 over the cardinality of n, so the number of players, sum over all the teams that did not include y, I. Oh shit, the editing is bad here. Okay, so it's fine. So all the teams that are inside the subset of teams that does not have I. Disjunct to normalize, and then this differential. So we can view it differently. So basically, it's 1 over the number of players over the sum of all the teams that did not include I. So let's say you are the player I, number I. So all the teams that do not have you with them, you get the worth of these teams S with you minus the worth without you. So with this difference, you get some kind of what does the I brings to a team, and it's really interesting in cooperative game theory, because it's a new value to quantify the solution, or the importance of a value when you have correlation between players. For example, a player with another might be struggling, like it can have a negative correlation with another if they don't like go well with each other. So with this marginal value being summed over something that goes nicely, so the Shapley values has other properties, but basically it quantifies the use of the player I in a certain game. And in particular, game theory shows that the sum of Shapley values in all the players, so if you go through the players, so what's the Shapley value of a player number 1, Shapley value of number 2, Shapley value of number 3, etc. It goes to V to the n, V of n, so V of all the players, and it goes to the worth of all players in the same team. And it's good because, as I said earlier, I expected 1, so obviously so I knew my cost function C1 to n was supposed to go to 1, because I know that. I'll explain a bit later why. With enough samples, so I'll explain it a bit later, but I tested my algorithm with multiple samples, like a lot, and I did not get 1 at all. So I knew there was something fishy, and this is the proof why I should have 1. Okay, and while I was doing some research about why I was wrong or not, something I learned is that in game theory, the Shapley values has been extended to other games. I'm not sure exactly what's the difference. It's called the Harsanyi dividend. So it identifies the Shapley values as being the Möbius inverse of V. So here, basically the Shapley value of I is just V. Is just the Möbius inverse of V to the I. So it's just a fun remark. So now Sobol indices. So now we drop cooperative game theory, And we go to statistics. As you've seen earlier, we have variance, we have conditional expectancy. So Sobol is a Russian mathematician. So he was thinking about some aspects of uncertainties, and he showed that if you want to estimate the variance of a conditional expectancy with respect to some variables, like when you have a lot of samples, you can approximate it with that. In particular, Martinez showed in one of his PowerPoint lecture that the conditional expectancy is a good measure of the importance of the value. So taking the variance of this actually gives a lot of information about the uncertainty. And the term measure is correct because it's a projection, yeah, onto a space. I'm not going to go too much in detail. It's correct. And this approximation comes from the fact that we assume a linear model. So like you perform a computational regression, you get the coefficient beta. So let's say you have an output y, inputs I, input x. So x is a vector or matrix. So like for example, in a lot of algorithm, you have a lot of inputs, like what's the cross section of this, what's the distance between two uranium atoms, or things like that. And so this is your input, and as output you can have like the neutronic flow in a certain region, and then you do a linear regression. So the goal was to quantify the importance of the variable xi with respect to a given result I. The problem with that is that certain inputs were cross correlated, meaning that x1 and x2 were correlated with each other. So the Shapley value in sensitivity analysis. So sensitivity analysis has multiple branches. One of their branches is variance analysis, which is the Sobol part. And recently, Owen had the idea to implement the Shapley value from game theory, but using the cost function that is a closed Sobol index. In particular, one can note that if you have x to be all the inputs, so a being 1 to n, so all the inputs, obviously I depends on x. Like it's obvious if you assume a linear model. If you pick all the x, then the expectancy of y is fully conditioned by the x. So then the variance of this is obviously zero. Is obviously zero. No, is obviously one. Is obviously one, and which is why we get the normalization condition from earlier. So now we give so the Shapley value for sensitivity analysis with a cost function being a closed Sobol index gives an estimation of the value without the effects of other values. So if you have x2 depending on x1, it's interesting to know how much x2 is making it vary independently. But this independently is in the sense of cooperative game theory, not in the sense of physics. Like it's not completely orthogonal, but it's in the sense of cooperative game theory. And it's frequent in particle physics, thermodynamics, chemistry, and electronics that some, like let's say in chemistry, that a chemical compound influence another, and you want to know the effect of that, the first one or the second one, and you want to be decorrelated, but decorrelated in the sense of game theory. So once again, I remind you my task. So it seemed really easy. And I thought I had a good understanding of it, like both in a theoretical part, in a computational part, and I want to bring your attention to this part in red here. So what I did is to calculate minus a, so 1 to the n minus the element that are in a, so okay. Calculate sigma on the elements that are minus a, so this thingy here. Then invert sigma to get sigma minus 1. Then we get a matrix of size A cross A. Then take sigma to the minus 1, and we also get a matrix of size AA, and we take the element AA. Wait, if we invert sigma, we don't get size AA, we get size NN. Oh, sorry, yeah, this is size NN, and then we take the A element, so we get size A to A. So when you do the matrix multiplication, you get minus A times A, so this junk here, A here, and here we get A minus A. So far it makes sense, right? It's fine, because if you've studied the matrix multiplication, you can do matrix multiplication if the left matrix, its right term here, is the same as the right matrix thing here. So this corresponds with this, and this corresponds with this correctly. So it was really fine, and it should have worked. But something I did not know is that this. The problem here is that you actually take the element AA and then you invert it. And how did I figure that out? It's because of the Schur complement. So I was looking at the proof of the approximation for the Sobol index, and I did not understand the proof. Like, it was really messy and just assuming some things. And I came to this article, and basically when you get the inverse of something, first you take the block part, the block D, and it's this block that you inverse. It's not you take the invert and then you take the elements that should be here. So I did not know that, and I was really shocked, because I did not know that. I was really sure that you had to invert first, then take the elements. But no, you had to take the elements first and then invert it, which was like really strange. But it comes from this, the Schur complement. And so the thing is that I think this I think this notation is really strange. Like, to me, it's obvious that you first take the inverse and then you take the A element. And I suggest that for people who work on this, to do parentheses and say sigma AA and then to the power minus 1, because it's really confusing. I think, in my opinion, I think it's confusing, and it can lead to problems in computations. So I'm really sad that I did not that I missed this. And you might say, oh, just look at the proof of this to this. And the thing is that this proof is not so obvious, because in lots of statistics books, when you look for the proof to go from here to this, they just do one step from here to here, and then they just spit this formula. They spit it, like, really. And I know this formula is true from, like, experience, but I can't show it. And when you do, like, the references linked in the proof from this to this, as one problem is that they also have this notation of Schur complement here. They have this thing, but wrote without saying which blocks. So you end up in the same situation in which you don't know if you first apply the minus 1 or you first take the block part. So that's all for this video. Thank you for watching. If you have any questions, feel free to ask them. Goodbye.